Okay, let me start today's class. Today we are talking about virtual memory, one of the most important abstraction that the operating system provides. By the end of this class, you should understand what address space is, how addresses get translated, and what the operating system does behind the scenes to make it safe and fast. In today's lecture, we will cover three main parts. First, we will talk about the core abstraction of virtual memory, which is address space. Then we will look at the core mechanism, address translation, and compare software and hardware methods. And finally, we will discuss some important OS issues translated to managing virtual memory. Okay, let's begin with our first topic. We are going to explore the fundamental abstraction that makes virtual memory possible, the address space. First, let's start with one question. What does memory virtualization mean? Usually in most modern computer systems, there is only one physical memory space, but there can be multiple processes running at the same time while sharing the physical memory space. In this case, the operating system wants to provide an illusion that each process has its own separate memory space. This process can be executed as if it utilized the entire memory. This is the concept of memory virtualization. By doing so, we can utilize the memory resource more efficiently and allow those processes to share the memory space in a safe and controlled manner. Next, let's talk about how the operating system utilizes the main memory in the early systems. In the early days, the operating system could load only one process into the main memory, like this figure. But this method led to poor resource utilization and poor efficiency. There are two reasons for this. First, most user applications cannot fully utilize the entire physical memory because the size of physical memory is too large for one learning process. The second reason is that it is difficult for one process to fully utilize the CPU resources. I mean, if a process tries to wait for an I/O operation, then it cannot utilize the CPU resources during that time. Then in this case, the CPU resources can be wasted. So this is a very inefficient situation in terms of resource utilization. To mitigate this problem, the operating system employed new execution models which are called multi-programming and time sharing. Under these execution models, the operating system can load multiple processes into the main memory at the same time. After that, the operating system allows each process to run on the CPU by switching between them. More specifically, in the multi-programming model, scheduling will be performed when the running process tries to wait for an I/O operation. In the time-sharing system, the scheduling will be triggered whenever a timer interrupt occurs. In this way, the operating system can increase resource utilization and efficiency. That is, this is a better execution model than the previous one. But these execution models also have a critical problem related to protection. just a minute. Related to protection. Let's see this figure. In this figure, the operating system has loaded three processes, process A, process B, and process C. But in this situation, one process can access the memory regions of other processes as well as the operating system, like this. So if this process has a malicious intention, then it can leak some private data from other processes or ruin the entire system by modifying some data of the operating system illegally. So we can say this situation is very risky in terms of system security. To address this problem, the operating system provides a new abstraction of physical memory, which is called address space. Under this abstraction, each process has its own separate address space, and it can access only the space at runtime. Let's take a look at this figure. This figure shows the address space of one learning process, and as you can see, this space contains everything related to the learning process, and it consists of several memory sections such as program code, data, heap, and stack. And in this example, we assume the total size of the address space for each process is only 16 kilobyte for simplicity of explanation. But actually, the real address space of a process is much larger than this one. For example, in a 32-bit computer architecture, the address space size is 4 gigabyte, and in 64-bit computer architecture, the address space size is 2 to the 64 bytes. Okay. So I mean the real address space of a process is much larger than this example. Okay, this example number is just for simplicity of explanation. Okay, then let's break down the components of typical address space as shown in this figure. The first one is code, which is where the program's instructions are stored. And the data section stores global or static variables. So these two sections are stored in the program file, and when the program runs, they are just loaded into memory as they are. That means their size is fixed. That is, it never changes during execution. And the third part is heap, which is an area for dynamically allocated memory. For example, when your C program calls envelope function, or your C++ or Java program uses a new keyword, that you are getting memory from the heap at runtime. And the last part is stack. This is used for function calls. In other words, it stores local variables, function arguments, and return address values needed to go back to the previous function. So compared to code and data sections, the heap and stack sections can grow and shrink while the program is running, like this arrow directions. And from now on, we can assume that there are only three sections: code, stack, and heap. This is just for simplicity of our explanation. This slide is perhaps the most important one for understanding the central idea of virtual memory. It perfectly shows the two different points of view. First, on the left side, we have the process perspective. That is, this is its virtual address space. So as you can see, it's contiguous block of memory that starts at address 0 and goes up to 60 kilobyte. And it has its code at the top, a heap that can grow downwards, and a stack that can grow upwards with the write free space in between. This is the illusion that the operating system provides to the process. Now look at the right side. This is physical memory, which is the reality of the hardware. And here you can see the operating system and processes A, B, and C are scattered around. So when a process is created, then a virtual address space is also created. And this virtual address space is mapped onto a free area in the physical memory. In this way, each process can share the physical memory independently. For example, in this figure, this virtual address space is mapped onto the physical memory region from 300 to 320 kilobyte to 384 kilobytes. So from the process point of view, it always accesses memory based on its own virtual address space. But actually, in the middle, there is something called the address translation mechanism. This mechanism converts a virtual address into physical address. So even though the process accesses memory using a virtual address, the system makes it access the actual physical memory behind the scenes. That's the role of the address translation mechanism, and it's really the key idea of memory virtualization. For example, if a process tries to access the program code area at 0 kilobyte in its virtual address space, then this address is actually translated to 320 kilobytes in physical memory. This is the basic concept of address translation. Okay, now let's take a look at the example program code. If you look at this code, it first prints out the name of the main function. In C language, a function name can also be treated as a pointer. So this line basically means that displaying the starting address of the main function. And next, the program allocates a memory object by using malloc function, and then it prints out the address of that object. And finally, this program prints the address of a local variable x. So when you run this program, you will be able to see the virtual address value of each object on the screen. And here is the output of this program. As you can see, we can check the virtual addresses of the main function, the dynamically allocated memory object, and the local variable x. And each of them belongs to different regions that is the code, heap, and the stack, respectively. Alright, now let's talk about goals of memory virtualization. There are three main goals. The first one is transparency. Basically, processes shouldn't have to know that memory is actually shared among many programs. From a programmer's point of view, it should just look like the process owns large, contiguous memory space by itself. So virtualization gives us a really convenient abstraction for programming. And the next is efficiency. We also want to use memory efficiently. That means minimizing something called fragmentation, which basically refers to wasted memory space. We will talk about fragmentation in detail later. And another part of efficiency is that address translation should be fast. Every time a process accesses memory, we need to translate a virtual address into physical address. So we will need some hardware support to make this translation fast enough. And finally, protection. We need to make sure that one process cannot corrupt another process memory or the OS memory. To this end, each process should be isolated. That is, so even if one process crashes, others keep running fine. But sometimes processes may want to cooperate and share part of their memory intentionally, and the operating system should allow that in a safe manner. We'll talk about this issue again later. Okay, then let's move on to the next topic, which is about address translation. Let's talk about how memory virtualization can be done efficiently and with control. Actually, memory virtualization uses a very similar strategy to what we saw before. That is the limited direct execution model. Remember that the goal of LDE was to balance efficiency and control. We let the process run directly on the CPU most of the time for efficiency, but the operating system still maintains control whenever special events happen, like traps or interrupts. In the same way, memory virtualization also needs to achieve both efficiency and control. And to do that, we rely on hardware support. For example, the hardware provides several important components like registers, TLB, which stands for Translation Lookup Site Buffer, and the MMU, or Memory Management Unit. So these hardware components make address translation really fast and help the operating system manage memory safely and efficiently. We'll take a closer look at each of these components one by one later. Okay, first we will talk about how address translation is done by hardware. As we discussed before, the operating system provides its process with its own virtual address space. But remember that the actual data is always stored in physical memory. So what it needs is a way to translate virtual address into the corresponding physical address. And this translation is done by hardware. But of course, the operating system still needs to get involved at key points to set up the hardware so that the translations can happen correctly. In addition, the operating system keeps track of which memory regions are free or in use, and it sometimes steps in to maintain control over how memory is used. Okay, then now at this stage, we make a few simple assumptions to make things easier. First, we assume that its process address space is placed contiguously in physical memory. Second, we assume that the address space size is smaller than the size of the physical memory. And lastly, we assume that all address spaces are exactly the same size. Of course, these assumptions are just for simplification. We will later see how to remove these assumptions one by one. Then now let's look at an example to see how address translation actually happens in a real program. Here we have a very simple C function, and inside this function there is an integer variable x, and this line is the one we will focus on. So what happens here is pretty straightforward. The program first loads the value of x from memory, and then it increments that value by 3, and finally it stores the updated value back into memory. Now let's see how this simple C statement looks in assembly code. Okay, this is what the compiler generates. That is corresponding assembly code for that one line. Here we can see 3 instructions, and let's assume that the memory address of variable x has already been placed in the EBS register. The first instruction, move well, loads the value of the variable x into the EAX register. And the second instruction is ADDL instruction, which adds the constant number 3 to that value. And finally, the third instruction is another move instruction, which stores the updated value back to memory. So again, we are doing the same 3 steps: load, add, and store. But this time you can see exactly how the CPU interacts with registers and memory to perform them. Okay, then now let's visualize where these instructions and data are actually stored in virtual memory. Okay, here is a simplified view of the process virtual address space. At the top, we have program code, and below that, the heap goes downward, and at the bottom, we have the stack, which goes upward. And these 3 instructions are laid out in the code section, and we assume the variable x is stored here at 50 kilobyte address. Okay, then let's trace what happens step by step. The CPU fetches the first instruction at address 128. That is the first instruction stored here, right? Then the CPU fetches this instruction from the memory, and then it executes this instruction by loading the value from address 15 kilobyte. As I mentioned before, the variable x is located here, right? And then the CPU fetches the second instruction at address 132, which is addl instruction. The addl instruction doesn't access memory. It just modifies a register value. And then the CPU fetches the last instruction at address 135. And here there is another move-well instruction like this. Then the CPU executes this instruction by storing the updated value back into address 50 kilobyte. So through these steps, the CPU repeatedly fetches and executes instructions, and each time a memory access happens, it goes through address translation to map the virtual addresses to physical addresses in memory. But here in this figure, we haven't actually seen the address translation yet, because these virtual addresses are not mapped to any physical addresses at this point. When the process starts running, the operating system needs to place that process somewhere else in physical memory. But that location is usually not at address 0. This is because that the lower part of physical memory is reserved for the operating system itself. So even though the process virtual address space starts from 0, it can't actually be placed at physical address 0. Therefore, the operating system has to place the process somewhere else in physical memory, not at address 0. So we call this behavior address space relocation, because the process thinks it starts at address 0 in virtual memory, but in reality it should be relocated to a different address in physical memory. Okay, here is a simple example. On the left side, you can see the virtual address space of a single process, and it starts from 0 kilobyte and goes up to 16 kilobyte, containing the code, heap, and stack, just like before. Now on the right side, you can see the actual physical memory, and at the top, the OS itself using the first 16 kilobyte region. So the OS decides to place this process somewhere else in physical memory. For example, starting at 32 kilobyte, like this. As a result, all addresses in this process are shifted by 32 kilobyte in physical memory. So this means when the process tries to access the address 0 in its virtual address space, then this address actually corresponds to a physical address 32 kilobyte. And similarly, at this process accesses 50 kilobyte in virtual memory to read the variable x, then this address should be translated to 47 kilobyte in physical memory. So this is the basic idea of address relocation. That is, even though its process thinks it starts at address 0, the OS can place it anywhere in physical memory without affecting how the process runs. Okay, now let's see how the operating system can actually relocate the process in memory. One simple way is software-based relocation, which is also called static relocation. In this approach, the OS rewrites the program before loading it into memory. That means the OS updates every memory address in the program to reflect where it will be placed physically. For example, if the OS decides to load this process at physical address 1000, then every address in this code will be increased by that offset 1000. So, for example, the address of the first instruction is 10, and 10 becomes 1010 like this, and 200 also becomes 1200. This is because the actual physical starting address of this process is 1000. I mean, here all memory addresses in the program were written assuming that the start address is 0. So all these address values must be increased by 1000 after loading. Similarly, if another process is loaded at 5000, then the OS rewrites again, adjusting all addresses accordingly. And after relocation, the addresses that have been placed in memory cannot be changed anymore. That's why we call this approach static relocation. Okay, then this time let's talk about the pros and cons of this approach. Basically, static relocation has one clear advantage. That is, it doesn't require any hardware support. So in this approach, everything is done by the operating system before program execution. However, there are also some big drawbacks. First, there is no protection between processes. That means one process can accidentally overwrite the memory space of the OS or other processes, or even read their data. For example, imagine a malicious programmer writes a large memory address value in their code. Let's say that this value is 1000. Let's say this value 4200. Then when the program is loaded with the base address of 10,000, then that address becomes 5200 in physical memory. That means the process can access the data located at the address of 5200. Which is actually outside its own memory boundary. So basically, it's accessing memory that doesn't belong to it. This is why static relocation has a big drawback. That is, it cannot enforce memory protection in this to address this situation. Okay, and second, when a process is loaded, its address space cannot be moved. This is the second drawback of the static relocation approach. So, if physical memory becomes fragmented, it may be impossible to allocate a new process, even if there's enough total free space. For example, in this figure, let's say there are currently two processes already loaded into memory, and now we want to load one more process. But the problem is that the memory space here is too small, and this other space is also too small. So even though there is some free space, we cannot fit the new process anywhere. However, if we could move the second process upward like this, then we could make one large contiguous block of free memory at this location, right? Then we could use that space to load the new process. So this situation is called external fragmentation, where we have small free spaces scattered around memory like this. Basically, when external fragmentation happens, memory utilization becomes very inefficient, and the static relocation approach cannot handle this situation very well. This is the second drawback of this approach. To overcome these problems, we use dynamic relocation, which is a hardware-based method using a component called MMU, which stands for Memory Management Unit. Basically, the MMU performs address translation automatically every time a process accesses memory. And it also enforces protection. If a process tries to access an invalid or restricted address, then the MMU raises exception, which is also called fault. And the operating system just needs to tell the MMU what the valid address range is for the current process. After that, the MMU takes care of everything during program execution. Okay, here is how it works in practice. Basically, each process has two special registers managed by the MMU, the base register and the bounds register. The base register indicates the starting point of the process in physical memory, and in this example, it's 32 kilobyte. On the other hand, the bound register defines the size of the process address space, which is 16 kilobyte. So the address space from 0 to 16 kilobyte in virtual memory is mapped to 32 kilobyte to 48 kilobyte in physical memory. This mapping is performed automatically by the MMU hardware. When the program starts running, the OS decides where in physical memory to load it, and then sets the base register accordingly. So whenever the program generates a virtual address, the MMU adds the base value to get the actual physical address. At this point, you can consider the physical address value is equal to the sum of virtual address and base address. And at the same time, the MMU checks whether the address is valid using the bounds register. The valid address must satisfy this condition. That is, the valid virtual address must be between 0 and the value of the bounds register. If this condition is not satisfied, then that means the address is invalid, so the MMU will raise the exception. Okay, then let's go back to our earlier instruction example. Here, the first instruction is located at virtual address 128. And if the base register is 32 kilobyte, then the MMU translates the address of the first instruction to physical address 32 South 896. That is the sum of this one and this one. And when executing the first instruction, it loads data from virtual address 15 kilobyte. Then this address value becomes 47 kilobyte in physical memory after adding the same 32 kilobyte base. This is how the MMU performs both relocation and translation dynamically. And there are two common ways to define the bounds register. In the first way, the bounds value simply represents the size of the address space, like 16 kilobyte in this example. In the second way, the bounds register holds the physical address of the end of address space. So in this case, it's 48 kilobyte. Either way, the MMU uses the base and bounds registers together to ensure safe and correct memory access for its process. So basically, there is no big difference no matter which method we use. Now let's look at what the operating system actually needs to do to implement the base and bounds approach. The OS must take action at three critical points. First, when a process starts learning, the OS has to find the free space in physical memory where this process can be loaded. Second, when a process is terminated, the OS must reclaim the memory used by the process so it can be reused later. And finally, when a context switch occurs, the OS needs to save and restore the base and bounds values for each process. So these three moments are when the OS directly interacts with the memory management hardware. Okay, then let's start with the first case, when a process begins execution. When a new process starts, the OS must find a room for its address space in physical memory. To do that, the operating system maintains a data structure called free list. That is, the free list keeps tracks of all memory regions that are currently not in use. For example, the first node here represents free space that starts at 16 kilobyte, and the second node represents another free space that starts at 48 kilobyte. So when a new process is created, the OS simply looks up the free list to decide where in physical memory it can place the process. Next, let's see what happens when a process finishes. When a process is terminated, the OS must put its memory back onto the free list. That means the physical memory previously used by the process can now be reused for future processes. If you look at this figure before termination, the free list contains only two regions, 16 kilobyte and 48 kilobyte. But after process A finishes, then the OS adds that freed space back into the list, like this figure. Finally, let's look at what happens during a context switch. Whenever the CPU switches from one process to another, the OS must save and restore the base and bounds pair associated with its process, and these values are stored inside the PCB structure. For example, on the left side of this figure, process A is currently running. and its base and bound registers are set to 32 kilobyte and 48 kilobyte. And when a context switch happens, then the operating system saves these values into process A's PCB structure, like this part. And then the operating system loads process B's base and bounds into the MMU. In this case, its base and bound registers are set to 48 kilobyte and 64 kilobyte. So in this way, this ensures that each process can only access its own valid memory region, even as the CPU switches back and forth between them. Alright, to summarize today's lecture, we talked about the fundamental concepts of virtual memory, focusing on address space and address translation. And in the next class, we'll continue this topic and go deeper into how virtual memory actually works. Okay, then that's all for today's class. Thank you for your attention, and I will see you next time.